Dear respected colleagues and participants, it's our great pleasure to present the results of our study entitled Study of the Sorption Process of Petroleum Products in Wastewater using Natural and Modified Bentonites. This work was carried out by our research group from Bukhara State University in collaboration with Kathmandu University. Currently, a lot of attention is focused on development of low waste or waste-free technologies as well as energy and resource-saving methods. Wastewater treatment plays a crucial role in achieving these goals. Traditional sedimentation methods used in industrial plants remove only suspended solids, while many harmful cations and anions remain in the water. As a result, the concentration of pollutants often exceeds maximum permissible limits. The scientific hypothesis of our study is that the use of natural sorbents, coagulants, and flocculants can significantly improve the efficiency of wastewater treatment by removing not only suspended solids but also harmful ions and heavy metals. In our experiments, we used natural bentonite obtained from the Navbahor deposit in Uzbekistan. It was subjected to three types of modification: thermal, chemical, and thermochemical. Commercial activated carbon was used as a reference sorbent. Additionally, reagents such as aluminum sulfate, ferrochloride, and sodium carbomethyl cellulose were applied as coagulants and flocculants. To simulate real conditions, we prepared synthetic wastewater containing petroleum products in three concentrations: 76, 140, and 265 mg per liter. Each sample was treated with 10 grams of sorbents at pH 6 with particles about half millimeter in size. The sorption process was studied under different duration of contact, 2, 4, and 8 hours. The efficiency was measured by analyzing the residual petroleum content using gravimetric methods. For the combined treatment, we used bentonite or kaolin with coagulants and flocculants followed by sedimentation. Key parameters such as pH, COD, BOD, sulfates were measured before and after treatment. These experiments allowed us to evaluate both the sorption performance of bentonite and the synergetic effect of its combination with coagulants and flocculation methods. Our aim was to investigate the chemical treatment of highly mineralized wastewater and to develop a technology that reduces salinity to permissible levels. Experiments showed that wastewater treatment using only coagulants and flocculants is often insufficient. For this reason, the introduction of highly sorptive natural materials such as bentonite and kaolin is necessary. According to our data, the optimal bentonite concentration for maximum removal of suspended solids is 3 grams per liter, with a mixing duration of about 20 minutes. Longer mixing times did not significantly improve the results. We also compared different treatment approaches: sorption only, sorption combined with coagulation, and sorption combined with coagulation and fluctuation. The third method demonstrated the highest efficiency, reducing COD, BOD, and sulfate concentration to much lower levels. This confirms that combining sorption with coagulation fluctuation leads to synergetic effects. The kinetic curves of wastewater treatment clearly demonstrate the combined method ensured faster and more effective pollutant removal compared to sorption alone. As a result, kaolin and bentonite were used in a 1-to-1 ratio with a total concentration of 2 grams per liter. For coagulants, we applied aluminum sulfate at half milligrams per liter and ferrochlorides at 0.75 milligrams per liter. As a flocculant, we use sodium carbamethylcellulose at 0.15 mg per liter. The kinetic variation of these treatments are shown in figure 3. The sorption process begins in the first 20 minutes and reaches maximum efficiency after about 3 hours. At higher concentration of petroleum products, the sorption capacity of bentonite increases proportionally. To better understand the behavior of bentonite, we carried out thermal and structural analysis. It was found that at 80 to 180 degrees, absorbed water molecules are completely removed. At 400 degrees, coordinated water is released, which increases the sorption surface by creating micropores. However, when the temperature exceeds 600, the crystal lattice of bentonite is destroyed, and it causes a sharp decline in absorption capacity. Infrared spectroscopy was performed to analyze the structural changes of bentonite after different modification. At temperature of about 8 and 900 degrees, we observed an exothermic effect, which indicates the destruction of bentonite structure. To study the main chemical and mineral components of bentonite, we obtained AR spectra of both the natural and thermochemically modified samples. The characteristic vibrations of the structural components are shown in figure 9 and figure 10. Bentonite did not show noticeable sorption activity for hydrogen or nitrite ions in the nitric acid solution. This was confirmed by the infrared spectra, where no characteristic absorption bands were observed. In contrast, the thermochemically modified bentonite showed clear structural changes in the spectra. We could see shifts related to hydroxyl groups, carbonate ions, and aluminum silicate bonds. These changes indicate that modification significantly changes the structure and improves the sorption properties of the material. To conclude, the maximum sorption capacity of bentonite is achieved through thermal modification at 400 degrees. This treatment increases the absorption surface and significantly improves wastewater purification. Our findings confirm that combining bentonite sorption with coagulation and fluctuation offers a highly effective and economical method for treating wastewater contaminated with petroleum products. Therefore, natural and modified bentonites represent a promising solution for environmental protection and sustainable development. Thank you for your attention.